Good afternoon. Today I will present the NeurIPS 2023 paper titled Survivor Permanental Process for Survivor Analysis with Time-Varying Covariates. This paper is about survivor analysis, but in a setting that goes beyond the basic Kaplan-Meier estimator and Cox proportional hazard model. The key issue is that in many real data sets, covariates are not fixed at the beginning of observation. They change over time. For example, a patient's blood pressure, a machine's temperature, or a customer's activity level can all evolve during the follow-up period. The central question of this paper is, how can we model event risk when covariates change over time and when their effect on risk are non-linear? The paper proposed a Bayesian non-parametric model called Survivor Permanental Process, or SurvPP, to answer this question. I will organize the talk in 7 parts. First, I will briefly recap survivor analysis concepts, and second, I will explain why time-varying covariates are important. And third, I will discuss the limitations of existing methods such as Cox pH, boosting, and random forests. Fourth, I will explain the main idea of SurvPP. Fifth, I will explain how the method is computationally scalable. Then I will summarize the experiments and results, and finally, I will give my own critical evaluation of this paper. My goal is not to reproduce every mathematical proof. Instead, I will explain the problem and institution and the method, the results, and what we should take away from this paper. Survivor analysis is about modeling the time until a target event occurs. The event can be death in medicine, medicine failure in reliability engineering, customer churn in business, or treatment failure in a clinical study. A key difference from the ordinary classification is censoring. In many datasets, we do not observe the event for every individual. For example, if a patient is still alive when the study ends, we do not know the exact death time. We only know that the event time is later than the final observation time. Two important functions are the survivor function and the hazard function. The survivor function gives the probability that the event has not occurred up to time t. The hazard function measures the instantaneous risk of the event time at t, conditional on survivor up to that time. Kaplan-Meier estimates survivor curves non-parametrically, and Cox proportional hazard model how covariates affect the hazard. This paper goes beyond that basic setting. Many classical survivor models start with static covariates. That means each individual is represented by one fixed feature vector, such as age, sex, or baseline diagnosis. But in many real-world settings, covariates are not fixed values. They are trajectories. In engineering, temperature, vibration, and maintenance conditions can change. In business, user activity and payment history can also change. This matters because event risk may depend on the trajectory, not just the baseline value. For example, the risk may increase only after a covariate crosses a threshold, or it may depend on a recent trend. If we use only static covariates, we may miss this dynamic information. So the problem is not just survivor analysis, the problem is survivor analysis with time-varying covariates. The paper positions itself against the 3 types of existing methods. First, Cox proportional hazard can be extended to handle time-varying covariates through a counting process formulation. So Cox pH is not restricted only to static features. However, Cox pH still usually assumes a relatively simple log linear effect of covariates on the hazard. This can be too restrictive when the true relationship is nonlinear. Second, ensemble models such as generalized boosted models and random survivor forests can capture nonlinear effects, but they often require many trees or learners. When covariates are measured frequently, the number of time intervals become large, and these models can become slow. Third, Bayesian non-parametric models such as Gaussian process-based models are attractive because they can model uncertainty and flexible functions. But naive Bayesian inference can be computationally expensive, especially if it relies on MCMC. So the design target of SurvPP is ambitious, handling time-varying covariates, model nonlinear hazard functions, keeping Bayesian flexibility, and remain computationally feasible. Before explaining SurvPP, we need to understand how the paper represents time-varying covariates. For each subject, the covariates are observed as a trajectory over time. The counting process format splits this trajectory into short time intervals. Within each interval, the covariate value is treated as constant. So, on subject to no longer represented by one row, instead, one subject becomes multiple Poseidon records. Each Poseidon record contains a start time, an end time, a covariate value, and the event indicator. This is important because the total number of Poseidon records, which the paper denotes by J, can become very large when covariates are measured frequently. But the number of actual observed events, denoted by N, is usually much smaller than J. This distinction is crucial. SurvPP uses all interval information, but its main optimization is tied to the observed event points. That is one reason why the method can be faster than many conventional nonlinear survival models. Now, let me explain the main idea of SurvPP. The key formula is lambda u t of t equals x squared of yu of t. Here, lambda u of t is the hazard of individual u at time t. The term yu of t is the time-varying covariance values of individual u at time t. The function x is the latent function drawn from a Gaussian process. The reason of the square is important. A hazard function must always be non-negative. If we directly model the hazard using an unconstrained Gaussian process, the output could become negative, which do not make sense. SurvPP avoids this by modeling the hazard as a square of a latent function. Intuitively, the model learns a flexible nonlinear surface over the covariate space. As the individual's covariates move over time, the hazard changes according to the value of this nonlinear function at the current covariate location. Um, Once we have the hazard function, we can compute survivor probabilities. For individual u, the survivor function is the exponential of minus the integral of x squared of yu of s from 0 to t. The institution is simple. The model follows the covariance trajectory of one individual over time. At each time point, it evaluates the hazard based on the current covariate value. That is, accumulates that hazard over time to estimate the probability of surviving up to time t. This is where time-varying covariates matter. The model is not asking only what were the features of the beginning. It is asking how did the risk evolve as covariates change over the observation period. That is the main modeling difference from static survivor analysis. This model is flexible, but flexibility alone is not enough. If inference is too slow, the method is not practical. This is why the paper's technical contribution is important. The paper shows that SurvPP satisfies the representer theorem. The main result is that the MAP estimator of the latent function can be written as x hat of y equals 2 times and the sum over n observed events of h or y and y tilde n times of vn. Here, y tilde n represents the covariance value observed at on event time, and H is a transformed kernel, so-called unequivalent kernel. The exact derivation is mathematically heavy, but the intuition is clear. Instead of optimizing over an arbitrary infinite dimensional function, the model estimates a finite set of coefficients associated with observed event points. This is the core of the paper. Um, the main contribution is not simply using a Gaussian process for survival analysis. The key contribution is making nonlinear Bayesian survival modeling computationally feasible for time-varying covariates through a counting process representation and the representer theorem. Now, the natural question is, why is this faster? The reason is separation between J and N. J is the number of pseudo records created by splitting time-varying trajectories into intervals. N is the number of actual observed events. In time-varying covariate settings, J can be very large because each subject may have many intervals. But N is usually much smaller. SurvPP still uses the interval information when constructing the equivalent kernel. However, the main iterative optimization is expressed in terms of event points. So when covariates are measured frequently, the algorithm does not become as slow as methods that repeatedly process as pseudo records during optimization. This is why the computational advantage becomes especially important for dense time-varying data. The paper evaluates SurvPP using synthetic and real-world datasets. The synthetic experiments include a log linear Hajar setting, which favors Cox pH, and a non-linear Hajar setting, where flexible models should help. For real-world data, the paper uses PBC with the depth of the event and SANAD with especially treatment failure as the event. It compares SurvPP with Cox pH, generalized boosted models, and a random forest-based survival model using dynamic AUC, testing log likelihood and CPU time. So the experiment tests both prediction, quality, and computational efficiency. The synthetic results show when SurvPP is useful. In the log linear Hajar setting, Cox pH performs very well because the data matches its assumptions. This shows that SurvPP does not always dominate Cox pH. However, in the nonlinear Hajar setting, Cox pH becomes weaker because the true covariance Hajar relationship is nonlinear. Here, non-parametric methods such as SurvPP and GBM perform better. The key result is that such SurvPP achieves performance comparable to GBM, but the much lower CPU time. This advantage becomes clear when covariates are measured more frequently. So the synthetic experiment supports the main claim. The real-world results are more nuanced. On the PBC dataset, Cox pH performs very strongly, especially in AUC. This suggests that the data may fit the log linear proportional hazard assumption reasonably well. In this case, the simpler Cox pH model is still very competitive. On the SNAD dataset, Cox pH is weaker, which suggests more non-linear relationship between covariates and hazard. Here, SurvPP performs better, and Cox pH remains much faster than GBM. So the conclusion is not that SurvPP always wins. It is most useful when covariates change over time, their effects on hazard or nonlinear, and the data is dense enough that computational efficiency matters. My evaluation is that this is strong methodology paper, but it should not be oversold. The strengths are clear. First, the paper directly addressed time-varying covariates. Second, it models nonlinear dependence between covariates and hazard. And third, it provides a Bayesian non-parametric formulation which can support uncertainty-aware prediction. However, the method should be has some limitations. First, RPP is mathematically harder than CoxPH and less interpretable. CoxPH provides simple coefficient-based explanation, while SurvPP relies on a latent Gaussian process function. Second, the experiments are mostly low-dimensional. The paper acknowledges that performance in higher dimensional covariate setting is still unclear. And third, hyperparameter optimization can be costly. The paper uses grid search for kernel parameters, which may not scale well in high-dimensional settings. And finally, comparison with modern deep survivor models is limited. The paper explains that many recurrent survivor models target a different setting, but broader empirical comparison should still make the paper stronger. This method is not limited to medicine. It can also apply to medicine reliability, customer churn, subscription, retention, and credit default prediction. So, it reliability engineering, temperature, vibration, and maintenance high history can change over time. A survivor model can estimate failure risk. However, SurvPP assumes that covariates are available as structured time-varying trajectories. So, before applying this method, we need reliable temporal covariate data. The model is powerful, but the data representation still matters. To conclude, the conclusion is SurvPP is a modern Bayesian survival model for time-varying covariates. The problem is addressed is that classical Cook-style models can be limited when hazard depends nonlinear on covariates that change over time. The key modeling idea is simple. Lambda u of t equals x squared of yu of t. The key technical contribution is the representer theorem, which makes estimation scalable by reducing an infinite dimensional function estimation problem to a finite optimization problem over event-related covariance points. The empirical lesson is balanced. SurvPP is not a universal replacement of CoxPH. When CoxPH assumption fit the data, CoxPH can still be excellent. But when covariates change over time, nonlinear effects matter, and the data are dense, SurvPP offers a strong combination of flexibility, Bayesian modeling, and computational speed. There is the main reference used in this presentation, and thank you for listening my presentation.